now we make calculating work is named calculation of prestressed bolt joint. Page number 19. Some words about this work. I repeat information from lecture. Main idea that sometimes we need to connect two elements. For example, like in our case, it is a cylinder and cover to avoid leakage of gas, liquid, maybe axial load, something else. And we should avoid gap between these two elements. So we need to calculate bolt prestressed force. It means that we need to connect these two elements, but not only connect. We should prestress it, because under the load, if we don't make prestress joint, if we don't do it under the load, bolt elongates and we have gap between these two elements. We should avoid this situation. That's why we need to pre-tight joint, and we should know how to calculate it, because it is a normal state in engineering practice. When you have any joint, and you should calculate what force you need to avoid leakage of something. We consider this situation when we know summary force and number of bolts. So if it's a force which load the only bolt, and we should know what the bolt diameter we need to take this load, because if we should create big load, we should know that our bolt can take this load. And initially bolt has a length LB equals LB0. It means that we don't tight this joint, and we have known length. And after prestressing, bolt elongates on value delta bolt, this value. And clamped elements length decreases on value delta joint. And these deformations are not equal, because they are proportional to stiffness of elements, stiffness of the bolts, stiffness of the joint. And we should prepare so-called bolt joint diagram to visualize this joint. We should use this diagram. At this diagram, we have a green line. It is a deformation of the bolt, and relatively yellow line, it is a negative deformation of joint. And after that, we move this line parallel at this point, and we have the triangle, and this triangle is named like bolt joint diagram. After that, after pre-tighten, bolts start operation in a load conditions we have. And under this load, bolt elongates one more on a delta, and the same delta, it is a result of decompression of joint. And I shown you in lecture that we should have this deformation less the delta joint deformation. Finally, we have diagram like this. Here you see this bolt deformation, this line is joint deformation. And after the loading by external load, we have such state that two not equal forces, Fz, this force additionally loads bolt, and delta F, this force decompressed joint. And we should create FP is prestressed force. Prestressed force enough to be greater than delta F. In such case, we have deformation and we have remnant force, which guarantee this both deformation and force guarantee gap will not present. So we need to calculate force, prestressed force, which will be greater than delta F. Delta F, it is F external minus Fz. Fz is Fz, it is a part of external force which applied to the bolt. So we have diagram like this. Here, they are the same. So let's start calculation. First part of our work to find prestressed force enough to avoid gap between elements. So let's start from initial data. So what variant? So Wei, your variant number 7.
Okay, teacher.
Omer, your variant number 10. Boris, your variant number 11. No one. Okay. So external force, kilonewton. It means that your force is 10,000, 12,000, 14,000, and so on. Then H, it is a thickness of the cover and cylinder. The same in our calculation, we make it easier. H the same for cover and for cylinder. Write it here, variant force H. After that, we'll write bolt material. Bolt material, you see it according to this table. And cylinder and cover materials. Write down there. Ready? Boris disappeared. Wei.
Yes, teacher.
You ready? Did you write?
Yes, I write down.
Okay. Amer,
Yes, sir, I wrote.
okay. Boris, are you here? Something wrong. Okay, we're going. Prestressed force we need may be found from this formula. And this formula, K, it is safety factor. And let's take it 1.5. 1.5 because it for may be used for constant and variable load. And he it is a, where is it written? Is a joint constant. It's a joint constant. We can't find it right now because to calculate joint constant, we should know these parameters: stiffnesses of joint and bolt or flexibility. That's why we need to use recommended values. Recommended values is from 0.1 up to 0.4. Let's take it 0.3 because it for steel bolts it's approximately 1 from 0.2 up to 0.35. So 0.3 it's approximately the same for all. And write down these parameters in a table page 20, parameter K 1.5, he 0.3. In such case, prestressed force, according to this formula, look, if he 0.3, 1 minus 0.3, 0.7, 0.7 times K is 1.5, so it means that F prestressed is 1.05 times your external force which is given. And this result put here. Kilonewtons. Then to find force which acts on a bolt, total force, Fp is prestressed force, we found it, and we should add Fz. Fz it is a part of the external force which loads a bolt additionally. So we need to find Fz. Fz is external force times bolt joint constant. So 0.3 times external force. And after that, we can find Fb, prestressed plus Fz. When we know force Fb, we can calculate diameter of the bolt. We need to take this load. Bolt works under tension as usual, and we should use strength condition on tension, and from this strength condition we can find d1. D1 is the inner diameter of the thread. What we need to know? Fb we know. Beta is 1.3 factor taking into account influence of the torsion. We don't know what is this not correct, very accurate value. That's why we use additional coefficient. It is calculated, it is not recommended. It is calculated, and it's third part of force. It is part of which create torsional load for bolt during the tightening. So beta is 1.3. Fb we know, pi sigma additional allowable. Sorry. To find allowable sigma, we should use formula like this. Sigma y is yield stress for bolt material, and S safety factor 1 to 3. Better if we take 2. In such case, we will have the only direction to change, take D1 standard. So sigma y you can take from this table. Material you know, sigma y is this column. So take sigma y and divide by 2. Result put here as we should take 2 sigma allowable sigma y divided by 2.
Sir, could you show me how to find S one more time, please?
S
Yes.
it is recommended.
Oh.
Look,
Which one should we choose? 2 or 3?
better take 2 because if you take 3 or something else, you calculate D1 and you can move to find standard up or down in table. But if you take less value, you should recalculate to check is it safety factor, acting safety factor enough or not. That's why I recommended take 2. In such case, when you take S2, you have the smallest safety factor. It will be the biggest allowable stress. If you have the biggest allowable stress, you have the smallest D1 maybe. It means that you should select standard threat guarantee greater than D1 calculated. That's why I recommend you take S2. Is it clear?
Okay, now okay.
And when you calculate S sigma allowable, you can calculate D1. But pay attention, you should use here sigma B in kilonewton. When you calculate D1, you should use Newton. So if you take FB 12 kilonewton, you should use here then 12,000. Let's calculate D1 and put result here, D1. If you calculate correct, your result should be from region, in region from approximately 8 up to 25 to 28 millimeters. If you use FB in Newton, sigma in megapascals, result will be in millimeter.
Excuse me, sir.
Yes,
For pi, which value you have to take? Pi,
pi
you
it's
see?
a pi, 3.15.
Okay, 3.14.
Oh, 14, sorry, 15.
Yes.
Sir, I found root of 52. It's little more than 7. Is it wrong?
Maybe.
Okay, I can try one more time. As you said, it should be more than 8 and lower than 20. Okay.
Yes.
Okay.
No, approximately, because if your result D1 less than 1 millimeter, sometimes when student made mistake and took FB in kilonewtons, result will be very small, less than 1 millimeter. That's why I said that it should be millimeters. So when you know D1 and we took sigma allowable smallest, it means that we should use D1 greater than calculated. At this table, at this table you see standard. Standard dimensions. I hope you know that any thread has one so-called coarse pitch and a number of fine pitches. For each coarse diameter, we have one so-called main coarse pitch, and here should be 2, 3, 5 fine fine pitches, but we use one coarse, one fine. And pay attention that this table is in increasing order. And your task, find nearest, closest T1 standard, which is greater than your calculated, and write what D and pitch for such variant should be. Write it D and P. T1 standard, D and P. For example, if you result, for example, 9 millimeters in D1, 8 and 6 less than 9, it is not correct. Next 10, it's greater. So in such case, I should take 12 with coarse thread, coarse pitch 175, and so on. Ready?
Okay, ready.
Okay. So when we know what both dimensions we have, we can calculate joint constant. Remember, we used joint constant to find prestressed force and to find Fz. And in both cases, we use recommended value. But when we know diameters, we can calculate correct value of joint constant. Let's do it. First, we should know lambda b. Lambda, it is a reciprocal value for stiffness, and flexibility of the bolt may be found like L bolt. E is modulus of elasticity. A1 area of the bolt. Let's consider these parameters. First, length of the bolt. We know that in deformated part, we have stresses and elongation in each cross section. And what L of the deformated part of the bolt? Of course, it should be two thicknesses H is thickness of cylinder plus height of cover cylinder, and 0.6 times H, where H is a nut height. It means that only 60% of the nut height takes part in deformation, or half nut and this portion are not deformate, are not deformating. That's why H and H we know they are the same. We need to know H capital. H capital is a height of the nut. Height of the nut may be taken from table 3. Height of the nut. According to D and P you selected, you should select range size and height of the nut and put there here S and H. This S and this S are not the same. Here is the safety factor. Here is the range size of the nut. Be careful.
So what about E? EB.
E, okay.
Yes. And
A,
F4.
just a moment. E, it's a modulus of elasticity, table 4. Modulus of elasticity, table 4. What's the material? For bolt we use or carbon steel or alloy steel. Carbon steel, I remind you that which is without the letters. Just a moment, I retune. These steels are carbon steels because no letters in designation. But if you use any letter, H, X is a chrome in Russia, and H is N nickel, and another materials. So these steels are alloy steel. So when you know what steel you have, you can take or carbon steel modulus of the elasticity or alloy steel. Pay attention that E, very big value, times 5, power 5. It means that 200,000 megapascals, very big value. And write it. Bolt EB next. A1. You can calculate it, but easiest way, write value A1 from this table and put it A1 here. When you know L, B, E, B, and A1, you can find flexibility. Pay attention that its value will be very small. And better if you write result in form where will be something times 10 minus 6. If you have doubt calculation result, you can download this methodic, and here you see calculation example. You can use this example like order of calculation and to check approximately your result. For example, L bolt in my examples like this, and result something times 10 minus 6. Write your result here. The only difference right here lambda B, lambda joint. Lambda joint. Lambda bolt relatively simple. Lambda joint a little bit more complicated. So a lambda joint can be calculated like this. H cylinder and H cover are the same. That's why in such case we can move it out from brackets. E we can take from table number 4. If your material is steel, I mean the material of the cover or cylinder, in such case you should take value 175, not 2, not 2.1. Steel casting, because cover and cylinder may be from
Yes, teacher. For everyone has to take 1.75.
no. I mean that if your material of cover or cylinder, just a moment. For example, cast or number 7.
For example, take 11.
You should take for steel casting, the same for cylinder and for cover. In such case, you should take steel casting 175. If cast iron 1.3, aluminum 0.7. And put these values here. E is cylinder and E cover. If they are the same, write 2 times. It's not principal. And then AE, its equivalent area. I told you in lecture that material into so-called pressures, cones of pressure, is deformated. Outside this cone, it is not deformated. That's why we should take this area like area which is deformated. And AE, it is a area of equivalent area. Equivalent area. D, it is DE square minus T0. T0, it is a hole diameter. Bolt is placed in a hole with a clearance. That's why we should take smallest diameter. Hole diameter is D0. D0 is D thread diameter, outside thread diameter, plus 1 millimeter. Plus 1 millimeter. So in such case, you can calculate AE from this formula, where DE, it is equivalent cylinder diameter. It is S plus half H. S, it's a range size. It is not safety factor. It's range size. Range size should take from this place, or if you miss this, table 3, range size. So you can calculate lambda joint. E we took from table 4. AE calculated like this. DE, this dimension, range size plus half thickness. And D0, it is D plus 1. And better if you write result the same like something times 10 minus 6. The same like here should be here. And if you calculate correctly, your area should be 100 millimeter square. And lambda joint less than lambda bolt. If lambda bolt, it is something times 10 minus 6, here should be less than, maybe not less, maybe 1, 2, but less than lambda joint. And the result, put d0, de, ae, and lambda joint. Now when we know lambda bolt and lambda joint, we can find He, joint constant. Lambda joint divided by lambda bolt plus lambda joint. Pay attention that we used form something times 10 minus 6 here, and we can neglect reduce on 10 minus 6, so easy way when we use lambda without 10 minus 6. And you'll see what he, in your case, really. It should be less than 0.4 and greater than 0.1. And the result should be here. Gentlemen, let's do in such way. We have 10 minutes, that's why we don't finish this work. Make at home calculations up to joint constant. To calculate it correct, you can use example. And step by step, you should check what your result, the same like here, algorithm, up to this value. And where you can take it from, I show you. DME labs bolts bolt V21. Clear?
Yes, clear, sir.
So download this file and step by step, like it is in the example, make this calculation up to find joint constant. Next class, we continue and finish this calculation, okay?
Okay, sir.
Yes, teacher.